Hi class. So we are starting a new chapter and this has to do with rates of reaction. And the first section is reaction rates and chemical equilibrium. So rates of reaction, everything has a rate to it. So for instance, we grow older and we grow older over a slow, it's a slow rate over time, where some things are a lot faster. For instance, food goes bad very quickly. And here's an example here of silver tarnishing, and this can take place over 5 months. Everything has a rate to it, and we're going to take a look deeper into that. So the first thing we need to cover is collisions. So let's talk about collision theory. Collision theory is for a reaction to occur, the molecules of the reactants need to come into contact with each other. So they have to get near each other in order for something to occur. This has to do with collision theory. A reaction takes place only when molecules collide with proper orientation and sufficient energy. So collisions occur all the time, but only a few lead to the formation of a product. So chemistry is a lot of misses more than hits, and there's a lot that goes into before even a reaction occurs, because they want to make sure that they can remove any barriers or obstacles to make the reaction successful. And one of the things is to look at collisions. Collisions, the atoms may interact, but if they're not oriented correctly, nothing's going to happen on this. So if we take a look at these pictures here, we are dealing with nitrogen and oxygen. Nitrogen and oxygen are diatomic molecules, so there's two. That's how they're found in their natural state. And we want to produce nitrogen oxide. So we got 4 examples here of a reaction of nitrogen and oxygen coming together, but only one of these actually forms products. And the one that forms products is because the orientation is in the correct way for the products to occur. So if you look here, nitrogen and oxygen are both vertically oriented, meaning more, think of standing up. And when they collide together, they produce nitrogen oxide and nitrogen oxide. Now, if you take a look at these are actually oriented in the opposite of what vertical is. So they are horizontal, meaning laying down. But this reaction occurs. Now, let's take a look at reactions that do not occur due to the incorrect orientation. So when we look at this one here, we have the same of what's matching up here. But along with collisions, the collisions have to give enough energy in order for the reaction to occur. And we'll get into what that energy is in a few slides. But if the reaction does not have enough energy, so when the collision happens, there has to be enough energy in that collision to allow this to happen. But if the collision does not have enough energy, then these molecules simply bounce off each other and go on their way. Nothing happens. If we look at the other one here, there's wrong orientation. They're both horizontal, and that's not going to lead to products of nitrogen oxide. So nothing happens again. And then here we have one that's vertical and one that's horizontal. Again, nothing's going to happen. So we have to have molecules that are oriented correctly and collide with enough energy as one of the factors for products to be produced. Now let's talk about energy. So orientation may not be enough. You must have enough energy in order to have, this energy has to be enough to break the bonds between the atoms of the reactants to form new bonds of the products. So think of climbing a hill. If you don't have enough energy to climb that hill, then you don't make it to the other side. And this is the same thing. You have to have enough energy, you have to be prepared enough to get over that very steep hill. Same thing for molecules. They have to have enough activation energy, or the reactions do not occur, even if there is, if they collide a lot and in the correct orientation. So if we look at this diagram here, this is an energy diagram, and what it does, its energy diagram, it plots energy from increasing from bottom to top versus progress of the reaction. And the graph starts with reactants of nitrogen and oxygen, then increases to the highest point, and then declines until the products are produced. This line levels out. So if we look here, this is one thing I noticed is that the reactants actually have lower energy than the products. So this is a very unfavorable reaction in the first place, because the products, you're going to need something to push these products to occur, because since this is lower energy, chemistry is all about stability and lower energy. It wants to stay like this. But let's say that we do have something, we add energy to this on top of, to make sure it goes over the activation energy. So we're going to need something to push over this hump in order for these products to occur. So there's going to have to be a certain amount of minimum energy in order for this to happen. And that's what the activation energy is. It's the minimum amount of energy needed to convert the colliding molecules into products. It has to have enough to break the bonds of the reactants to create the products and new bonds. And if there's not enough energy to go over this activation energy, then nothing occurs. The molecules again just bounce off each other. So our next slide has to deal with activation energy. Even when a collision has a proper orientation, there still has to be a sufficient energy to break the bonds. So we have to have three conditions in order for a reaction to occur. The reactants must collide, they must come in contact with each other, and they have to be oriented in the correct alignment in order for this collision to occur and to actually have the reaction occur, so that they can break and form bonds. But along with the orientation, there has to be enough energy to get over that energy of activation to allow the bonds to break and create new bonds. So now let's take a look at reaction. So we've covered conditions for a reaction to occur, but now we're going to look at rate, meaning time. How long does something take? The rate or speed of a reaction is determined by measuring the amount of reactant used up over a certain period of time, or a product formed over a certain period of time. Me being in the lab, I have worked on a reaction that took 8 days to finally produce product. So it can take a very long time. It could take even longer than that. It could be almost instantaneous. But you need something as a start so that you can see how something's progressed. So we're interested in the change in concentration of reactant or product over time. So one of the factors that can affect the rate of reaction, there are a few that we're going to discuss. Reactions with low activation energies go faster than reactions with high activation energies. What this means is that the hill is not as steep. It might be lower, which makes the molecules, it doesn't require a lot of energy as something like this to produce products. So a lower activation energy is one of them. And then for any reaction, the rate is affected by changes in temperature, changes in reaction concentration, and adding a catalyst. So rate of reaction, temperature, we've already covered temperature with gases and so forth. So let's talk about kinetic energy. As temperatures increase, there's an increase in kinetic energy as well. So in this case, we're not necessarily talking about gases, we're just talking about molecules at no physical states here. But the energy of the reactant molecules will actually start moving in more and more together. Think of, you're boiling water. The water starts getting more vigorous because more energy is being added and it's affecting the molecules. They're forcing them to collide together because they're becoming faster and faster. So they're trying to get, this extra energy is putting something in them to make them move faster. So as they move faster, they collide more often. More makes them collide with more energy. So if you want a reaction to occur, you might want to look into increasing a temperature to cause the collisions more to produce the to produce the products. For every 10 degrees Celsius that's increased in temperature, most reactions approximately double. Think of cooking food. If you're cooking food, you can heat it up. If you increase the heat, the food will be done faster. The quality of food might not be great, and you probably burned it, but we're not interested in that here. We're just looking at time. And in this case, if you want to cook something faster, you increase the heat to get it done quicker. So let's take a look at this one. This is a rate of reaction involves reactant concentration. When there are more reactant molecules, more collisions that form products can occur and the reaction goes faster. So basically increasing the reactions, the concentration of reactants means that they have more opportunity to collide with each other because there's more of them. Think of an elevator filled with people. The more people that are in there, the more you have a chance of probably colliding with somebody if you're trying to get to the other side of the elevator, or a subway, if you think of it that way. Where if it's less space, if it's more spacious, then you may not collide with people as much. You can avoid them because there's a lot more room. So by increasing the concentration, we're also increasing the chances of collision. So let's take a look at this picture here. Let's call blue the sphere A and the red sphere B. And they end up coming together to producing a makeup of sphere A and sphere B. Now we have 4 possible collisions here, so let's take a look at the first one. The first one has one sphere of A and one sphere of B, which means they only have one possible collision. But on the second one, let's say we have 2 spheres of A and one sphere of B. Now they have 2 possible collisions with sphere B. And now if we add 2 spheres of A and 2 spheres of B, there are 4 possible collisions that occur. So by increasing the concentration to a point that you're forcing interaction, and the more collisions means that there's more possible chances of the correct orientation to produce the products. And the last one is rate of reaction, catalysts. So adding a catalyst speeds up the rate of reaction by providing an alternate pathway that has a lower activation energy. When activation energy is lowered, more collisions provide sufficient energy for reactants to form product. During a reaction, a catalyst is not changed or consumed. So let me explain this in a way that makes sense. Let's say you go to a Dodger game and you don't know where your seats are. They have those ushers there that help you. So instead of walking around trying to figure out where your seats are, if you go to an usher, the usher knows exactly where you need to go, and they save time by getting you to your seat, and then they leave. That's exactly what a catalyst does. A catalyst is not part of the reaction. It's not consumed. It's not changed. It doesn't play into the reaction. It simply speeds up the reaction. So it gets you to your seat faster than if you had, or even a concert. Let's say you're at a concert venue and you don't know anything about where your seats are. An usher will get you there, and now you've just saved a lot of time to get to those seats. And then the catalyst leaves and it helps somebody else and does the same thing. A catalyst does not play a part in the reaction itself. It simply lowers activation energy. It creates a new pathway and lowers the activation energy to allow the reaction to occur. So if we take a look at this graph here, so here's an energy diagram. It plots energy increasing from bottom to top. So we can see this here. And then versus the progress of the reaction. So think of time. Graph rises from the energy level of the reactants, right here, to the 2 possible peaks. So we have 2 possible peaks, both, and here's the products, okay? The higher peak indicates the activation energy for the uncatalyzed reaction. So this is a very big hill. Think about if you have to run over a hill like this. The lower peak indicates the activation energy for the catalyzed reaction. So again, reading the definition, it creates an alternate pathway that has a lower activation energy. So it lowers that. So this is a new path, which means that the molecules don't have to have as much energy as they would here. So it makes it easier, and more of them can go over this hill compared to this one. So by doing that, it allows more, less energy needs to be used, and this may take way more time for this to happen. This is less time. So it increases the time and it lowers the activation energy for a reaction. But the catalyst is not used. It's not used up and it's not changed, which means it can be used over and over and over again. So factors that affect reaction rates, here we have increasing temperature, more collisions with energy of activation. So they have enough energy because that kinetic energy is with them, allowing them to speed up. Increasing reactant concentrations. The more you have you increase the concentrations, think of more concentrated instead of less dilute, then they have more chance of these atoms coming together and being oriented correctly. And adding a catalyst lowers the energy of activation. So think of lowering that hill that you would have to run over, which makes it easier to run over and you can get to this other side quicker. So let's take a look at some examples of how to, let's answer these. Indicate the effect of each factor listed on the rate of reaction as I increases, D decreases, or N no change. So we're going to look at this reaction here. And looking at this, we're going to answer these. So A, raising the temperature, would that increase, decrease, or no change? Well, if we look here, increasing the reaction, the temperature increases the rate of reaction. So that's going to be increases. Now, what if we remove O2? If we remove one of the reactants, we are actually decreasing the chances of the reactants colliding with each other, which means there's not as much here. We want to add more, not less. That decreases the chance of collision. So that's going to be decreasing. And adding a catalyst, we've already covered this, so this you should have said increases. And lowering the temperature, oops, sorry, went wrong, decreases. So remember, raising the temperature increases. So if you're lowering the temperature, that is the opposite of it. Things slow down. You don't have as much energy, and it definitely lowers the kinetic energy, which means that you don't have enough energy to get over the energy activation energy. Okay, state the effect of each on the rate of reaction as I, D, or N. So decreasing the temperature. So what do you think that is? That's going to decrease. That was just the example that we covered here. So lowering the temperature is the same as decreasing the temperature. Removing one of the reactants, we covered that with oxygen. If you remove the oxygen, you are removing a chance for more collisions, which means you're removing the chance of more product happening. So that's going to be decreases. Sorry, this thing moved all over for me. Adding a catalyst will increase because that's that usher that's taking you to your seat and saving you time of being lost. Placing the reaction flask in ice. This is the same as decreasing the temperature. Oops, both of those weren't supposed to go, but that's okay. And increasing the concentration of a reactant. Of course, that means that's the opposite of B. You want more, you want it more concentrated, means more chance of collisions and more chance of collisions with the correct energy and the correct orientation.